So I started my timer a little bit late because Izzy distracted us. So I think it looked like got most of this in on the previous video. Again, there's no x direction forces, there's no y direction forces on this cube. That leaves us just down to the z direction. So coming up in the positive z direction, I've got P2 times xy. I've got minus the weight, and I've got minus P1 times xy. And again, those are all in the z direction. Okay. Now, since it's all equal to 0, and I'm really just dealing with the z direction, let's not worry about the vectors anymore. Let's just say in the z direction, I've got P2xy minus the weight minus the P1 xy. And we don't have to worry about the directions anymore because we're just in one direction now. Okay, now, what do we know about the weight? Well, weight is equal to mass times gravity, right? Now, if I've got a cube of fluid here, that's what we're looking at. And we want to know, how can I find the mass of this cube? I need to find the weight of the cube. Well, how do I find the mass of the cube of fluid? Well, if I know what kind of fluid it is, I might be able to find the density. So the density times the volume is going to give me the mass. Can I find the volume of this cube? The easy question is can I? And normally the answer is yes. Yes, I can find the volume of this cube. Now the harder question is how? How do I find the volume of this cube? And that's not too hard, right? The volume of the cube I can find by base times width times height. And in this case, that is x, y, z. That gives me my volume. So if I substitute that in here, 0 is equal to P2xy minus rho xyzg minus P1 xy. Now, to keep the mathematicians of the world satisfied, and I would say these cancel out, but to keep the mathematicians of the world satisfied and happy, we say, well, because they're non-zero, we can divide every term by x and y. X and y are non-zero. So we can divide every term by x and y, and therefore we can simplify this expression. That's good for the mathematicians. For the engineers, we say, well, they just cancel out. X and y cancel out because they're in every term, and I'm okay with that if you guys are. 0 is equal to P2 minus rho gz minus P1. And the way we would write that is P2 minus P1 is equal to rho g, and here's how we write this in this textbook. We say Z1 minus Z2. And we understand that Z equals what we call the elevation. So in this text, we use this sign convention, where we say Z represents the elevation within the fluid, right? So Z represents the elevation in the fluid. As you increase elevation, you'll decrease the pressure, and that makes sense when you go diving and submerging in water or liquid. As you increase your elevation in the fluid, you decrease the pressure. If you increase your depth, right, in many texts, and if you're joining us not from my class, you're in a text that they say, well, no, P2, delta P is equal to rho G delta Z. And that's okay. There's nothing wrong with that. You just have to understand the rule. Anytime you've got a simple equation, right? Remember, where does this equation come from? This equation comes from back here. Right? This vector equation, this guy from this free body diagram, Newton's second law simplifies to this or this. Anytime you have a simple equation, it's going to have rules associated with it. If you write it this way, where delta P is equal to rho G delta Z, that means Z is equal to depth. As depth increases, pressure increases. Our text likes to write it this way, where we say delta P is equal to rho G Z1 minus Z2, where Z is referring to elevation. As you increase elevation, you decrease pressure, whereas you decrease elevation, you increase pressure. If you increase depth, you increase pressure. It depends on what do you want to call Z. This is how I will approach it because this is how your textbook does it. Understand that there are some textbooks that will do it this way, and that's okay as long as you understand the rules. You should always understand the rules associated with an equation before you use it. In our line of work as engineers, that's how we kill people, is when we use an equation that we don't understand how it works. Literally, that's how we kill people, unfortunately. Okay? So just be aware of that. Here's the rules. If z is elevation, it's z1 minus z2. If z is depth, which is not how I will work it, because it's not how your text works it, but if z is depth, it's z2 minus z1. Okay? Okay. Let's see here. So there's this graphic in your text. And again, this is from Chengel and Bowles, Thermodynamics and Engineering Approach. If you're not familiar with it, but my students are familiar with it. The idea here is they're saying that if you come across at the same elevation, they're saying here that the pressure at all these points, here so I see what I'm seeing. The pressure at all these points here, A, B, C, D, E, F, G, is all the same. It's this atmospheric pressure, right? This surface, this little symbol right here, this little triangle with the lines below it, that tells you the pressure at that point is equal to the atmospheric pressure. Okay? That's what this little symbol right there is. So they're telling you if you want to know the pressures at points A, B, C, D, all these, I would take this point right here, this is the atmospheric pressure, and add to it the rho GH to get down there. Now, how do we know that? Well, it's based on this expression. Okay? It's based on this expression. Let's say that I say that this is open to the atmosphere. And let's say that I want to know the pressure down here at this point. Let's say this is 2. And we'll say this is 1. Right? So these have z values. You've got z2 and z1. Remember, z, we're using z to refer to elevation. So if I want to say that this is, let's say the surface is 0, then this is minus h, if this is height h. So if this is 0, then this is minus h, because this is below. I've decreased my elevation to get here. Right? Or you can say that this is h if you say this is 0. If I say point 2 is 0, anything above that is positive, so this is h. Okay, and so what we're saying there is if I take the pressure at point 2, subtract from it the pressure at point 1, that's equal to the density of the fluid times gravity times z1 minus z2. Well, if P1 is equal to 1 atmosphere, well, we'll just say P atmosphere, then we can say P2 is equal to P1 plus rho G Z1 minus Z2. And it doesn't matter whether I plug in here 0 minus the negative H, or if I plug in here H minus 0, I get H. So this is equal to P atmosphere plus rho G H. The same thing they're saying right here. Pressure at all these points, because it increases linearly as you move down, the pressure at all these points down here at column H is going to be the initial pressure starting here, plus the rho GH, the increase beyond the atmospheric pressure to get down to that surface. Now, notice they have said down here that they're saying pH is not equal to PI because you've got a mercury column right in there. Okay? So you have a mercury column down there. So it's just water to get down to point I. It's just water here. But you've got a different density. So what happens if I've got a different density? Well, right? So let's say that I've got a different density down here. Well, what I need to know is let's say this is Z2, this is Z1. I would need to know this elevation here, Z3. And I would need to know this elevation down here, Z4. Right? So if I say that this is, I don't know, let's say this is 0. No, let's make this easy. Let's call this 0. So everything above that, so let's say this is, I don't know, we'll say HC. We'll say this is HB. We'll say this is just H. Okay, so if I've changed my 0 value now. Yeah, I've changed my 0 value now, right? And so let's say P4. Now I can't go directly from P4 to P1 without doing some cool stuff. Now I can do that. This is water. And down here I've got mercury. We'll just use Hg for mercury. Okay. So I can't go right straight to P4, but that's what I want. I want 0.4 down there. Now, right there on there, I've got surface 3. Right here at the floor, I've got surface 2, and up here, I've got surface 1. Okay. I can't go straight to P4 very easily. Well, it's not hard, but let's do this. We know this. We've got this equation. This allows me to get between one column of fluid, from one location to another within one column of fluid. Okay? All right, so let's do this. Let's say I already know that P2 is equal to atmospheric pressure plus rho GH. We found that earlier. Okay? Let's get to P3. I know P3 minus P2 is equal to rho G. And it's going to be, if this is 3 minus 2, then this is 2 minus 3. Okay? So this is equal to P atmosphere, P3 is going to equal P2 plus rho G. Well, let's plug them in here. Let's say Z2 we're going to call HB minus HC. Alright? And so if I plug these in here, then I'm just going to have... So again, you can kind of see, we can find this. This is P atmosphere plus rho GH plus rho G, and then the difference between these two elevations, HB and HC. So I can find that then. Now to get to P4, I can go through P3. P4 minus P3 is equal to the density of mercury, because it's mercury through there, times G. And this is going to be Z, if this is 4 minus 3, this is 3 minus 4. Right? So I can plug this in here for P3. The atmosphere plus rho GH plus rho G, and then the change in elevation between those two locations, 2 and 3. Right, so the increase to get to this lower elevation. And then add to it the density of mercury. The pressure increase as a result of the mercury column, which is just going to be, let's see, this is HC, because it's HC minus 0. Right? Okay, so as you move through a different column of fluid, the point there is if you move through a different column of fluid, you need to do your pressure difference between each point that you can compute your pressure difference, and then string those together. Now there are methods you can write one long equation with that, and that works if you understand that. If you want to memorize all the rules associated with that, that's a lot of rules to memorize. But if you're comfortable with that, you're welcome to look that up. Okay. What else we got? I got to keep moving here. I know I'd like to talk a little more about that, but hopefully I get you started. Look at some problems, get some practice in on that, and we'll go from there. Now I'm going to set Pascal's law aside. This is a nice stopping place. You're welcome to look in the text about what he says about Pascal's law. It's kind of cool, but it's not required for what we're doing here. Okay, so all right.